Hey everybody, let's take a look at a couple of really good applications now of some of the major concepts that we've seen in this chapter. And the first one is optimization, and that's what I'm going to walk you through in this video and then the next one as well. So remember, so much of what we did in this chapter involved finding when functions have those key points, finding when functions are hitting those maxes, whether it be a relative max or relative min or an absolute max or an absolute min. And so there's a lot of practical problems in everyday life where we can apply calculus to figure out when things are optimized. And so we'll look at a few of those types of problems right now. So example one, I said a math teacher wants to build a rectangular play area for his children using the back of his house as one of the sides of the play area. If he has 50 feet of fencing, what dimensions should he use to maximize the play area? And what is that maximum area? And this is actually a question that you don't necessarily need calculus for. So let's just start by visualizing it a little bit, and then we'll look at some ways that you can approach it, and then we'll finish by talking about how you would use calculus to solve the problem. So to begin, I guess I'm just going to sketch my picture here, and this is going to be the back of the house right here, and the back of the house is one of the sides of the play area, and so the play area is going to be rectangular. So it's just going to look something like this. And we can see that since this is a rectangle, that we have a dimension here, call that x, and then we have a dimension right here, we'll call that y. And so our goal in this question is to maximize the play area given certain constraints. We have 50 feet of fencing. But one of the things that you want to do in all of these questions is you want to ask yourself, what is the goal? What are you trying to optimize? This section is called optimization, and so you need to ask yourself in each question, what are you trying to optimize? And here we are trying to maximize our area. So that means I'm going to come up with an area equation. And so if I'm trying to maximize this area, I can see that my area is equal to just x times y. Okay, and I can also see that another constraint in this problem is the fact that I've got 50 feet of fencing to work with. So even though I want to maximize the area, and the area is going to be x times y, I need to figure out the best x and the best y given the fact that we've only got 50 feet of fencing. And so if there's 50 feet of fencing, then that's another equation that I can come up with, and that equation would be x plus 2y is equal to 50. So this is what I call the primary equation in this problem, and this is what I call the secondary equation. And so what we can do, we don't need calculus to do this, is we can take our secondary equation and isolate y, plug that into our primary equation, and then we have a primary equation in terms of a single variable. So if we do this, you could see I would bring the x to the other side and then divide by 2. So I would get y is equal to 50 minus x divided by 2. And so my area equation, the thing that I am trying to optimize, the thing that I'm trying to maximize, would be equal to x times 50 minus x divided by 2. And so let's go into the calculator right now and let's graph this. I just want to show you that we don't need calculus to do this. So I'm going to say y equals x times, we have parentheses, 50 minus x, and then I'm going to divide by 2. And let's hit graph and see what we get. And it probably makes sense when we hit graph that you're going to get something that really isn't going to look great, because when we are thinking about the constraints and the information that we have in the problem, and then we're thinking about also what our window is set at right now, it's probably not ideal to visualize what's happening in the problem. And so you can try things like zoom fit and things like that. I might just go into my window and say, you know what, let's go with an x min from 0 up to, I don't know, I guess we could go all the way up to 50. It's probably not necessary, but you know, if we went from like 0 to 50, and then if you think about some potential areas, you know, with some dimensions that you might have in here, you could see that you might want to go up into the hundreds for your y's. And so let's say that y min is 0 and y max is, I don't know, I'm just going to say 500 right now. And let's go to the graph and see what that gives us. So we go to the graph and we get an area function that clearly has a maximum somewhere in here. And so if we are solving this question graphically, what we could do is we could say second calc, and we could go to maximum, that's number 4. And left bound, you could put a number into the left. It looks like it's at our max right there though. So let's just go a little bit to the left side. And then we'll go a little bit to the right side. And then we will press enter and enter again. And you can see the maximum is right there at x equals 25. So you get x equals 25. And y is equal to 312.5. Now this y is not the y that we have right here, right? This y represents our area. So our max area, the max area is equal to 312.5. And so if we needed to figure out our other dimension here, we can go back into this secondary equation and just plug x equals 25 in. You're going to get 50 minus 25, so that's 25 divided by 2. So that would be y is equal to 12.5. So we just solved this question not using any calculus whatsoever. But in a second, I'm going to show you how we could have used calculus. One of the things that I'm trying to also emphasize, though, is we don't necessarily always have to resort to calculus just because we have the ability to work with it. Sometimes algebra does the trick. And it's always a good idea to keep this rule of 3 in mind, where we're solving something graphically, numerically, or using calculus. So if we're solving it numerically, it would have just been going into a table of values. And so let's go into the table and just observe in that table where your y values start to be maximized. And as I'm scrolling down here, you're looking at that thinking, okay, well, I know that my x value's got to be bigger than, what I've got so far. And then finally you get to x equals 25, and you could see that y is at 312.5 now. So looks like it's continuing to move there, but you get the idea. So you can just look at the table, and you can see from the table the x value and the maximum area at that particular x value. And then once you get that, the only thing that you would need to do is go back into your one of your original equations, that secondary equation, to figure out another one of your variables. So we look at it graphically, we look at it numerically, and then sometimes we're going to look at things, and a lot of times, right now, we're going to look at things using calculus. And so if we're going to solve this using calculus, this is what it's going to look like. We are going to take this primary equation that we have here, this area equation, and I'm going to simplify it a little bit. So let's distribute that x through. So we have 50x divided by 2 and then minus x squared divided by 2. And we know from calculus that we can figure out when we achieve those peaks like what we saw in this problem. And you might remember the only thing that we needed to do to make that happen was to figure out when our derivative was equal to 0. Now sometimes your absolute maxes and mins would also be at endpoints of intervals, but in a lot of questions like this, the point of interest where we are going to be optimizing is going to be both an absolute and a relative max or min. So basically what I'm suggesting is one of the themes in this section is to simply take the derivative and set it equal to 0. So if we find the place where we have that horizontal tangent line where the derivative is equal to 0, then that's going to lead us to our solution in this problem. So I'm going to take the derivative, and the derivative of 50x over 2 is just going to be 50 over 2, which is obviously just 25. And the derivative of minus x squared over 2, you bring that 2 down, it cancels, you just get minus x. And you would literally set that equal to 0 and solve, and you'd get x equals 25. Now, earlier in the chapter, what we would have done is we would have also said, okay, let's confirm that x equals 25 is in fact a relative maximum. And so we would have tested representative values from the derivative number line into the first derivative. And so if I took a representative value less than 25, you could see it would be positive, and then greater than 25, it would be negative, confirming that x equals 25 is a relative max. But we really don't need to do this step a lot of times in this section. Many times, simply the process of taking the derivative and setting it equal to 0 is going to be what we need. But at the end of this, after you do the calculus, you will need to go back into that original secondary equation that we formed. And so if you plug 25 in, again, it leads you to y equals 12.5. And then when you have both x and y, you can multiply the two of those together to get your max area of 312.5. So you can do this graphically, you can do this numerically by looking at a table, or you can do this using calculus. And I would almost argue that calculus might be one of the fastest ways of doing this sometimes. Instead of tinkering with the calculator and all of that, you can get your function in terms of a single variable, differentiate it, solve, and that's pretty much it. A little bit of back substituting and you're done. Okay, in the next video what I'm going to do is I'm going to walk you through a few other examples of this optimization process. Now, here it is all listed out. I am not, in those future videos, I'm not going to say, let's do step 1, step 2, step 3, step 4, step 5. What I'm going to say is, I'm going to talk you through it the same way that I did this last example. And so you can see what's going on behind the scenes is this structure. You know, we're assigning variables to the problem. We are finding a primary equation, the thing that we're trying to optimize. And we also need a secondary equation, usually to make a substitution into the primary equation to make the primary equation in terms of a single variable. There's sometimes some domain issues that you need to think about, but for the most part, it's all about a primary equation, the thing that you're trying to optimize, getting a secondary equation so that you can get the primary in terms of a single variable, and then step 5 here, where we are essentially doing the first derivative test, where we take the derivative and set it equal to 0 and solve. So hopefully this kind of gives you a nice overview in this video. In the next one, we'll look at a few more specific examples of what you're going to see in the homework and what you could see on the test.